Hi folks, the next topic we're going to learn about are solutions. And before we start getting into the specific definitions that deal with solutions, we need to talk about mixtures first. So a mixture is a physical blend of two or more substances. They are not chemically combined. It's not a chemical combination, it's a physical blend. When you have a mixture, there are two different types of mixture you can have. You can have a heterogeneous mixture, which is not uniform in composition. And what that means is that the components are not evenly distributed throughout the mixture. So a pizza would be an example of a heterogeneous mixture. If you have a bite of pizza, then you might get a pepperoni on that bite and a green pepper on this bite, and a slice of onion on this bite. Not every bite is identical. The pizza is not uniform in composition. Every bite is slightly different. A homogeneous mixture, on the other hand, is a mixture that is completely uniform in composition. Every time you take a sample, the components are exactly the same. An example of a homogeneous mixture would be sugar water, salt water, where every drop of the salt water in the glass has the same composition. Solutions are homogeneous mixtures. They consist of a solute dissolved in a solvent. Solute dissolved in a solvent. So I've got two more vocabulary words here. But before I get into those two vocabulary words, I just want to again stress the idea that solutions are homogeneous. They are uniform throughout. That is what makes them a solution. So let's look at these words solute and solvent. Solute is the substance being dissolved, and it is generally present in a smaller amount than the solvent. The solvent is the substance that does the dissolving, and it is present in a greater amount. When you dissolve a solute in solvent, it becomes a solution. And often in chemistry, we do deal with solid solutes and liquid solvents. However, it does not have to be that way. You can have a gas solute. Gases can dissolve in liquids. For instance, there's dissolved oxygen in water. That's how fish can breathe. There's also dissolved carbon dioxide in beverages. So you can have gases. You can even have liquids dissolved in liquids as well. Similarly, the solvent does not have to be a liquid. You can have solid solvents as well as gaseous solvents. But often in chemistry, we are talking about a solid solute and a liquid solvent. Usually in chemistry, or quite often, we specifically are dealing with a liquid solvent called water. It is the most common solvent that we'll use in chemistry class. So it's important to know the term aqueous solution to mean a solution in which water is the solvent. Water contains some sort of dissolved substances inside of it. Solvation is the process of dissolution, where something becomes dissolved in a solvent. So this process can be called solvation or dissolution. It's the process of dissolving. And when solvation happens, first the solute particles are surrounded by solvent particles. So in this example, water is made up of one red oxygen atom and two white hydrogen atoms. So you can see we've got lots of water molecules around. And here we've got sodium chloride or some other ionic substances where we have positively charged ions and negatively charged ions. So the solute particles become surrounded by these solvent particles. And then those solute particles are separated and pulled into solution. Okay, so the center ions here can't be pulled into solution until the particles towards the outside of the surface are pulled into solution. So this chloride ion will be pulled into solution before this chloride ion is. That actually brings us to the next thing we're going to talk about, which is what factors affect the rate of dissolution. As I said, particles near the outside of the chunk of solid that you're trying to dissolve here will go into solution more quickly than ones that are buried inside the solid chunks. Therefore, surface area of the solute plays a role in the rate of dissolution. The more surface area a substance has, the quicker it can dissolve. And one clear example of that would be dissolving sugar in your tea. If you've got little granules of sugar, those will dissolve faster than if you have a big lump of sugar cube. Another factor that will affect the rate of dissolution is agitating the solution. So stirring, for instance, or shaking will help the substance dissolve more quickly. And that is why people use a spoon or a stirring rod to stir to stir sugar into their coffee or tea. The third thing that affects solvation is heating the solvent. If you add sugar to your iced tea, you will find it takes much longer to dissolve than adding sugar to your hot tea. Sugar dissolves much faster, solids dissolve much faster when you heat the solvent. The opposite is actually true if you're trying to dissolve a gas, but we'll be mostly focused on solid solutes in this class. There is a fourth factor, since I mentioned gas, there's a fourth factor that can affect the rate of dissolution if you're dealing with gases only, though. Increasing the pressure increases the rate of dissolution, but only if you're dealing with a gas. So, how do you know whether something will dissolve in the first place? We talked about what might make something dissolve more quickly or more slowly, but some substances don't dissolve in solvents at all. Why does this happen? There's a rule or a phrase called like dissolves like, and that means that two substances that are like each other are more likely to dissolve in each other than two substances that are less like each other. And this alikeness is to do with polarity. We learned about polarity back in Module 3 when we learned about bonding. And chemicals with similar polarities are more likely to dissolve in each other. So for instance, if you have a nonpolar solute, it will dissolve in a nonpolar solvent. If you have a polar solute, it will dissolve in a polar solvent. But you can't mix and match, like a nonpolar solute will not dissolve in a polar solvent. So you need to match polarity in order to have a solute dissolve in a solvent. This like dissolves like idea is important in real life. This is how soaps and detergents work. So soaps and detergents have a polar head. There are carbon-oxygen bonds, and oxygen is electronegative, so it has a partial negative charge, and it pulls electrons away from carbon, which is left with a partial positive charge. And then the soap and detergent molecules have a long nonpolar tail. This nonpolar tail is attracted to oils and greases that you're trying to wash off of your hands or off of your dishes or off of your clothes. But then this polar head is attracted to water. So your oils and grease are kind of stick to this long non-polar tail and then can be washed away in water because of the polar head of the soap. So if you've got a mixture, how do you undo the mixture? How can you separate a mixture? Differences in physical properties can be used to separate mixtures. For instance, filtration is one that you may be familiar with if you ever brew coffee using a drip coffee machine, or almost any kind of coffee ends up trying to filter out the coffee grounds from the coffee liquid. But filtration is a process that separates solid from liquid or aqueous solution. Okay, so you have to have a heterogeneous mixture, not a solution, in order for filtration to work. If you take salt water and just run it through a filter, you're still going to have salt water. The salt pieces are too small. The salt ions are too small and just pass through the filter. So this only works with a heterogeneous mixture. Like sandy water, you could remove the sand from the water. And when I say the word phase, I mean any part of a sample with a uniform composition and properties. So like solid, liquid, gas, and aqueous solutions are all different phases. So filter paper, like a coffee filter or other material, can be used to separate solids from liquids. Solids can't pass through the holes in the filter because they're too large, and they stay on the filter, and that is called the residue. So that would be the coffee grounds if we're talking about coffee. And then liquids and any dissolved particles pass right on through the filter, and we have the liquid that's left behind, and we call that the filtrate. The filtrate. It is the liquid or aqueous solution that has been filtered. Distillation is another process that can be used to separate a mixture, and distillation is used to separate components of a mixture based off of difference in boiling points. Distillation is used when you have a homogeneous mixture, when you have a solution. And distillation works because you can boil a liquid to produce the gas form of the liquid, or a vapor form, and then you can condense it back into a liquid separate from any other components that have a different boiling point. For instance, you could use this process on tap water. Tap water has dissolved minerals in it, and you can get pure water out of tap water by taking that tap water mixture here in a round bottom flask, heating it to boiling. The water turns to steam at 100 degrees Celsius, and then that steam passes through this condenser tube. This condenser tube has an inner tube that the steam passes through, and an outer jacket called the condensing jacket that you run cold water through. So the cold water doesn't touch the steam directly, it just chills the steam to cool it back down below 100 degrees to turn it back into water. So the steam passes through the condenser, turns into water, and drips into a Erlenmeyer flask here to collect the pure distilled water. And any dissolved minerals or any salts or any other substances dissolved in the water are left behind in this round bottom flask. Pure water moves over, is collected over here in the Erlenmeyer flask, and any impurities are left behind in the round bottom flask. So just so you can get that in your notes in words, what I just talked you through. The tap water is heated in the distillation flask, forming water vapor. The vapor passes through the condenser, which is surrounded by cold water and cools back into a liquid. And then the liquid water is collected in a flask. Any minerals that were in the tap water stay behind in the distillation flask because they have very high boiling points. You can use any differences in physical properties to separate a mixture. For instance, if you had a mixture of aluminum nails and iron nails, how could you separate those? Think about that for a second. If you had a mixture of real wood mulch and rubber mulch, how could you separate those? When you're approaching a separating mixtures problem, there's some strategies you can use to kind of think about how to approach these problems. What I do first is I just list the properties of the different components of the mixture. Each different part of the mixture, I list as many properties as I can. I find differences in the properties, and then I try to take advantage of those differences. For instance, maybe one substance floats and another substance sinks. For instance, the wood mulch and the rubber mulch. The rubber mulch will sink in water and the wood mulch will float in water. So you could separate the wood mulch from the rubber mulch by dumping it into a tub of water and separating it that way. Magnetic versus non-magnetic. If you have iron nails and aluminum nails, the iron nails are magnetic and the aluminum nails are not. So you could use a magnet to separate the two types of nails. If you have something that's soluble and something that's insoluble in a mixture, you could take that mixture, mix it into water. The soluble stuff will dissolve, the insoluble stuff won't, but then you can use a filter to filter out the insoluble material. And a difference in boiling point. As we saw, if you've got a difference in boiling point, you can use distillation to separate the substances. I hope this helped.